Okay, welcome back to this course on stereochemistry. Right now, we are towards the end of this course, almost towards the end. We are discussing now the dynamic stereochemistry, and under dynamic stereochemistry, we have come to the what is called asymmetric synthesis. Asymmetric synthesis, sometimes also called asymmetric, because the synthesis is carried out by induction of some group or some center. So, it is sometimes called asymmetric induction. Okay. Now, last time we have seen what are the different types of reactions, stereospecific reactions, stereoselective reactions, and we have gone through the definition. Now, asymmetric synthesis I have also defined, but I have also made a comment that nowadays this stereoselective synthesis and asymmetric synthesis are continuously used as if they are the same. There are slight differences when the stereoselective synthesis is meant to form a chiral compound. When a stereoselective synthesis reports the synthesis of a chiral compound. So, if it leads to the synthesis of a compound in chiral form, then that is called that is a stereoselective synthesis. This is also called in traditionally it was called stereoselective synthesis, but it falls under the broad category of asymmetric synthesis. So, again I repeat that whenever you are making a compound and you see that the end result of your reaction is that you are making a compound in chiral form, in one chiral form, then we say that you have achieved a stereoselective synthesis. But that is same as saying that you have achieved what is called an asymmetric synthesis. Now, asymmetric synthesis is basically the broader term, and the definition again I repeat. Last time I told that if you are generating an asymmetric center in a chemical reaction, and if so that should lead to the formation of either R or S. If one of the configuration predominates in the reaction, that means it is predominantly produced, then we say that we have achieved an asymmetric synthesis. So, in a molecule, if you are generating a chiral center, and if you generate the chiral center in one enantiomeric form, then that is called asymmetric synthesis. Now, in this definition you see that it says that a chemical reaction or a reaction sequence, it may not be achieved through one chemical reaction, it may be achieved through a series of chemical reactions in which one or more new elements of chirality are created in a substrate molecule. And now we are broadening it a little bit, we are not sticking to only one center, there may be several centers that are created in the molecule, in the substrate molecule, and which produces the stereoisomeric products. Now, if it is only one center, that will produce an enantiomeric product. If it is if you are producing multiple chiral centers, then the products will be diastereomeric, and if these products are produced in unequal amounts, then that is called an asymmetric synthesis. But as I said, also commonly known as stereoselective synthesis of chiral compounds. Now, stereoselective synthesis has two meanings. One is that addition of bromine to a double bond, that is also stereoselective, but that does not produce any, that produces only DL mixture. Okay. And so, chiral compound is produced, but that is produced as a DL mixture. This is also stereoselective reactions, but this does not fall under the category of asymmetric synthesis. When you can make the compound in one chiral form or partially pure chiral form, then that will be called a then that stereoselective reaction will fall under the category of asymmetric synthesis. I hope it is clear. Stereoselective reactions leading to the production of chiral compounds falls under the category of asymmetric synthesis. Okay. But asymmetric synthesis is a general term, that whenever you make a center, chiral center, or a series of centers, and if they are produced lead to stereoisomers in unequal amounts, then that is called an asymmetric synthesis. Now, asymmetric synthesis, I told you that what is the basis of asymmetric synthesis, that the molecule, that the transition state leading to the product has to be diastereomeric. Otherwise, the rate of formation of the two isomers will not be different, because what you aim at is that the rate of formation of the diastereomers should be different, then only you can get different products, different amount of products. Okay. If the transition, if the activation energies happen to be same, then it will lead to a racemic mixture. So, the target of asymmetric synthesis is to make the gap between the transition states for the two diastereomers or for the two ultimately it may lead to enantiomer, but the gap of the diastereomeric transition state, the transition state has to be diastereomeric, and when either you are leading to enantiomer ultimately or diastereomer, that does not matter, the reaction has to go through diastereomeric transition state, and the bigger the difference, the greater will be your success in asymmetric synthesis. Success means the diastereomeric excess, that means the excess of one diastereomer over the other, or the enantiomeric excess, that is the excess of one enantiomer over the racemic form of the mixture, they will be of higher value. Okay. Now, I gave you here that how to make this. One way of making diastereomeric transition states is to have a built-in chiral center already. If you have a built-in chiral center and which is in a particular form R or S, then what happens? The transition states that will be generated by the approach of the nucleophile to this, suppose the X is oxygen, to the carbonyl, carbon will be diastereomeric to the transition state which is obtained when the nucleophile approaches from the bottom side. Okay. So, now we have two different transition states. So, there is a possibility that the two isomers will be formed in different amount. Okay. Now, there are how do you consider is which one will be the major product, can we predict, and I gave you certain rules that yes, there are certain scientists who have tried to predict that what will be the major product if the substrate configuration is known. That means, if the chiral center that is already pre-existing is known. Now, in the board here I have also introduced one term, that is induction, asymmetric induction. See, whenever this reaction takes place, whenever you are adding a nucleophile to this carbon, because of diastereomeric transition state, and if the transition state happen to be quite different in energy, then you will get one compound in much excess over the other. And we say that this is due to the fact, why it does happen? Because it is due to the fact that this carbon center is present. So, we say that this carbon, asymmetric carbon, is having an induction on the asymmetry that is generated on this carbon. So, that is why this is also called asymmetric induction. So, induction of an asymmetric already present asymmetric group on a carbon which is becoming asymmetric during the reaction. So, this is also called asymmetric induction. So, induction takes place. So, that means two different isomers that will be created from here, addition of nucleophile will be of different proportion. Okay. Now, as I said that which one will be more, which one will be less, there are certain set of rules. One set of rules was given by Cramp, DJ Cramp, and according to him that if the, see, there will be three groups apart from this carbonyl attached to the stereogenic center. Now, this is only true for a system where the carbon is adjacent alpha to the, when the carbonyl is alpha to the, or the stereogenic center is alpha to the carbonyl, okay, then only this rule is applicable. If it is little bit far away, then this rules does not hold. So, we are only sticking for the compounds where there is an alpha stereogenic center attached to a carbonyl system. And what it says that this will take a preferred conformation where the oxygen will be flanked by the small and the medium group, and that puts the large group eclipsed with the R group, that is the other group attached to the carbonyl. And now, according to Cramp, that if that the nucleophile approaches preferentially from the side of the smaller group. And so, if this approaches preferentially from the side of the smaller group, what will happen? The product will be your LSM remains in the same position, only the nucleophile comes and this becomes a nucleophile. This is the OH and that will be the R, R will be shifted on this side. Okay. And while it comes from the opposite side, that means which is not the preferred one. So, you get the other isomer. These are the, by the way, two diastereomers. So, you have a diastereomeric excess, or you have what you have achieved is a diastereoselective reaction, and this diastereoselective reaction is due to asymmetric induction by this chiral carbon. Okay. Now, this is what is Cramps rule. Now, there are other rules. Falcon and N, they differed from Cramp. They said the actual preferred conformation is one where the large group is perpendicular to the orthogonal to the carbonyl group, and that is the preferred one. So, if you have the same compound, so according to Falcon and N, so you have to put the large group perpendicular to the carbonyl R axis. Okay. If you take a Fisher projection, a Neumann projection, and then what happens? You are left with S and M, and see this is equivalent to this. How do you know? Because the carbonyl is placed on the top. So, what you have to do? You just see on seeing from this side, what is the direction of motion as you go from L to M to S. So, that is clockwise. So, L to M to S. So, once you put L, you know this is M, this is S, because that should be clockwise. So, that is the easiest way to conceive this. You do not have to think much. If you put the carbonyl, then just see from this side and what is the sequence as you go from L to, or the direction as you go from L to M to S. And this is see, there are two possibilities now. L can be orthogonal on this side also, but that puts the M on the right in front of the R. So, this is because of more steric hindrance here. So, this will be less favored and this will be favored conformation. So, now the carbonyl, now the nucleophile attacks here on this molecule and the OH goes there and the nucleophile comes here. I told you about the Birgit-Dunich principle, that the nucleophile actually approaches around 107 degree, which is close to the actual angle after the once the reaction takes place, when the carbon changes the hybridization from from sp2 to sp3. So, that is the Birgit-Dunich trajectory. Okay. So, it should actually approach from around 107 degree like this. Okay. So, carbonyl will remain almost in the same position, only the R will shift here and the nucleophile will come here. So, that is Falcon and N model. Now, there may be systems where both the rules are not applicable as per the earlier system. See, if you have a system where there is a dipolar group, a chlorine, where is this is called a dipolar model. So, already there is a dipole, that is the carbonyl, and suppose the next adjacent carbon, that means the stereogenic center, has a chlorine. So, now if you have a chlorine, so what happens? These two dipoles will tend to be aligned in an anti fashion, and that gives the most stable conformer. Okay. So, this is what is Cramps model. So, Cramps said that Cramps model. So, earlier Cramps said that L should be opposite to the carbonyl, but now according to this model, X should be opposite to the carbonyl in order to have less repulsion. So, ultimately if that is the case, then wherever be the S, from that side the nucleophile will attack and you will get the product. Okay. We will do some problems now to show the application of this. So, this is also called Cornforth. I think this was given, Cornforth improved Cramps model in this dipolar system. In case of Falcon, the same thing is there. If you actually try to apply Falcon's model on this, according to Falcon, that if there is a earlier Falcon's model, we have seen that the large group has to be placed orthogonal to the carbonyl. In case of the halogen, which is a polar group, so you have to put so they have modified their hypothesis and said that the chlorine, or if there is any dipole like this, then that dipole has to be placed orthogonal to the carbonyl. So, in that case the large group is not the dominant factor, it is the polar group which takes the orthogonal position to the carbonyl. Okay. Interestingly, both the models lead to the give rise to the same products. Now, another system or another situation that can happen, that in the chiral center you have a heteroatom and which is in a position to form a chelate complex when the reagent approaches, because many of these reagents are like methyl lithium or metal mediated reagents like methyl lithium, butyl lithium or titanium compounds. So, in that case what happens, your heteroatom, even if it is whether it is large or small or medium, you have to place it syn to the carbonyl, so that this chelation is possible. Okay. So, now if you transfer it to the Cramps model, so in this Cramps model, modified Cramps model, which is called Cramps Chelation model. So, what you have, this is the carbonyl. In the original Cram, L should be opposite to the carbonyl. In the polar dipolar system, the dipole should be opposite, that polar group should be opposite to the carbonyl. In case of groups which are able to form chelate like the heteroatoms, then the heteroatom should be syn to the carbonyl, and if that is the case, then whatever conformation you get, that the nucleophile will come from the side of the small group. So, this is an example which is not drawn according to the Newman, but this you can say that there is a center which is chiral center and there is carbonyl, and then you have CH2OH. So, in this case obviously this titanium reagent will form a complex in this direction, and now you have the small group here on the top and the large group, comparatively larger group at the bottom. So, the nucleophile will approach from the top face. Okay. So, this is an example of that Cramps chelated model. Okay. Finally, there was another system. I told you that Cramps model is applicable to systems where carbonyl is alpha, where the stereogenic center is alpha to the carbonyl system, where the stereogenic center is alpha to the carbonyl system. Now, you can have a system where the reacting carbonyl is quite far away, interestingly, in this molecule. Now, this is, by the way, is a compound which is derived from, this is called, if R is equal to phenyl, that is called phenyl glyoxylic acid, or you can say it is an alpha keto acid in general, an alpha keto acid. And if you make an ester with an alcohol, so you get an ester linkage and a pure carbonyl linkage, and the whatever R group you have, it may be phenyl, it may be other groups. Okay. Initially it was done, the experiment was done with phenyl, R was phenyl. Now, what happens, even if this chiral center is far away, now there is a rule which is called Prelog's rule, that this molecule is somehow influenced by the presence of this carbonyl. And what Prelog says, that now this molecule will adopt a conformation in which this carbon and the large group, carbon large group bond, this bond will be syn to the carbonyl carbon. Okay. See, there are two carbons, carbonyl carbons, one is the ester carbonyl, another is the plain carbonyl. Okay. This is ester carbonyl. So, what he says, that the carbon and the large group bond should be syn to the ketone carbonyl. Okay. And then if you add a Grignard reagent, suppose R dash MgX, then you have now two other groups, small and medium. So, the Grignard reagent will now approach from the side of the small group. This was called the Prelog's rule. You have heard of Prelog, because Carl Ingold Prelog. Prelog is a very famous well known stereochemist, and he was awarded the Nobel Prize for his work on stereochemistry, including all these things. So, Prelog's rule, where he started, and this Prelog's rule became very important, because earlier days it was very difficult to know the configuration of naturally occurring compounds. I told you the naturally occurring compounds exist in one enantiomeric form. So, if you have a chiral alcohol, so it was a tough job at that time to know the configuration, exact configuration of the alcohol, whether it is in the R form or in the S form, because the rotation, I said rotation has no connection with R or S. So, it was Prelog's rule which was applied. So, if you take the alcohol, make this alpha keto ester and then do the Grignard reaction and see what is the end product of this, and if you can analyze the end product, then if you do backwards, finally you can get the configuration of the alcohol. So, we will do all these in this lecture. Okay. So, let us do, because unless you do problems, these things will not be clear. Okay. First, we will see the Cramps, application of Cramps model. So, Cramps, the normal model, the first model that was given by Cramps. Suppose we do one problem, we take a compound which looks like this, and this was reduced with sodium borohydride. The question is, what is the measure product? Okay. What is the measure product? So, how do you do it, solve it? Only the first thing you do, you have to draw a Newman projection. Okay. Put the carbonyl and then here is a methyl. So, it is a methyl ketone. Okay. And then you have to put the bigger groups, the biggest group, that is the phenyl, which is anti to the carbonyl, because this is not a case of chelation, this is not a case of polar substituent. So, you can apply the Cramps normal model. Okay. And then you have two groups, methyl and hydrogen. Now, this methyl is actually, it is written in Fischer projection. So, this methyl is alpha, this hydrogen is also alpha, and this phenyl is beta. So, now if you look from this side, you can tell that the methyl, phenyl, methyl, hydrogen, that is actually going in a clockwise direction, and you have drawn the Fischer Newman projection such that this carbon is at the top. So, same thing will be maintained. So, you have phenyl, then methyl will go into this side, sorry, not here, methyl will be on this side and hydrogen on this side. So, that is the, because your phenyl, methyl, hydrogen is in clockwise direction. Okay. And then, so once you have fixed that, so this is your the preferred conformation. Now, you know that your nucleophile, see, which is suppose the borohydride, we have said. So, borohydride complexes with this, and then it approaches from the side of the smaller group. So, this is the small and this is the medium. So, preferential attacks takes place from the side of the medium group. So, now what you get is your bottom three groups remain the same, the methyl, the H and the phenyl. Only thing you have to do some changes in the, so that is OH, this is methyl, you have to follow the Bargy-Dunich principle. So, carbonyl remains almost in the same position, pushing the methyl here. Now, question is, what is this compound? So, you can, so this is the measure product, that is you can stop here, but if you want to know whether it is 3O and erythro, that you can work out by putting the 3O erythro in the zigzag conformation. 3O erythro has a problem, I told you that in the Fischer projection you have 3O erythro nomenclature, which does not match with the zigzag conformation. Okay. So, let us or you can now you can say syn and anti, that will be actually better. So, in syn and anti, what you do, you have to place the carbon chain in the opposite in a zigzag fashion. Okay. So, put this methyl here, the phenyl there, and the OH. So, first check the methyl here, then OH there and H here, and the other the phenyl remains at the same position. So, hydrogen and this is methyl. Now, you see that if you draw a zigzag conformation, so basically the methyl, then this and the phenyl. So, this is phenyl, this is methyl, and then you have this is the scenario. So, in methyl you have, when you look, you have OH to the right. So, OH to the right and H to the left, and in the phenyl you have H to the right. So, you have H to the right and your methyl is to the left, that means alpha. So, that means you are getting this is in the books, it is saying that this is the 3O compound. You can say this is the 3O, but mean this is the zigzag nomenclature. Okay. So, that is the main chain. So, 3O, or you can say this is the anti conformation that you get. Okay. So, that takes care of this Cramps normal model. Now, if you take the Chelation model, if you take the Chelation model, suppose or the dye. So, suppose I have this tertiary butyl CO and then hydrogen, ethyl and chlorine. Okay. So, the way to do it, I will not do many problems, I will just do it. The way to do it is that you have to see from that side. So, the carbonyl goes there, butyl goes there, and now the chlorine is on the bottom. You have to put the chlorine at the bottom, because that is the polar, you have to use the polar model. So, other two groups will be here, other two groups, and again I said that better see what is the directionality. If you go from, suppose I go from chlorine, then I come to hydrogen, then I come to ethyl. So, that makes, I have to see from this side, and that makes chlorine, hydrogen, ethyl clockwise. So, chlorine, hydrogen, ethyl clockwise. Okay. Chlorine, hydrogen, ethyl. So, I am seeing it from this side, sorry, this is this is chlorine, hydrogen, ethyl, that is anti-clockwise. So, I have to put the anti-clockwise, hydrogen, ethyl. Again I repeat, I see from this side. So, first it is chlorine, then I come to hydrogen and then I go to ethyl. So, that is anti-clockwise. So, this anti-clockwise is maintained, and this is the preferred conformation, this is the small group. So, now the nucleophile will approach from the side of the small group, and you can, I am sure you can get to the product. Only careful, you have to be careful while converting this into the Fischer. Okay. I was almost making a mistake. Na? So, this chlorine, hydrogen, ethyl is anti-clockwise. So, chlorine, hydrogen, ethyl you have to make anti-clockwise. So, if you follow that, then there should not be any problem. So, likewise you can do the Chelation model, everything. So, if you know how to draw the convert one form into the other, I think situation will be handled much in a easier way. Okay. So, we have seen that this asymmetric induction, how does it control the stereochemistry of compounds, where stereochemistry of compounds, it is a very specific group of compounds where the carbonyl is present adjacent to a stereogenic center. This stereogenic center then induces asymmetry, while the nucleophile is delivered onto the carbonyl. Okay. And the next session we will try to work out the Prelog's rule. We will do some examples on Prelog's rule, how the absolute configuration of alcohols can be obtained with the use of this rule. And by the way, before the advent of the X-ray crystallography, this Prelog's rule was becoming very important in solving natural product structures and stereochemistry. Thank you.